In this section, we're going to be really focusing on just a lot of vocabulary and trying to identify some of these three-dimensional figures. Now, so you want to pay close attention to the names and how we name specific three-dimensional geometrical figures. So first of all, we've talked about simple and closed before. A simple closed surface has a connected interior, has no holes, and it is hollow. So of these, you see these 6 drawings down here. Some of them are simple and closed, some of them are not. Actually, these are not simple and closed. This one violates the definition because it has a hole in it, and this one violates the definition because it doesn't have a connected interior. As you're drawing this, you would have to go back over where you and cross back over your line in order to draw it all in one setting, and that violates the rules. Crossing back over. Um, Now, it says this separates the space into 3 sets or 3 areas. All of your points on the surface on the outside, think about as if you were going to paint this. That would be our surface. Then all of the points on the inside, which is our interior, and then all of the points on the outside, which is the exterior. So it breaks it into 3 different spaces. If we talk about a solid, we're talking about all of the points on the surface along with the interior. So as if we were painting the outside and then filling it up inside with something. That would be considered a solid. Now, polyhedron is a simple closed surface made up of polygonal regions or faces. It also has vertices where the edges meet, and edges are where the sides meet. Now, the plural of polyhedron is polyhedra, and 2 of these are polyhedra, 4 of them are not. These 2 are actually polyhedra because they meet the criteria for our definition. It's made up of polygonal regions or faces. So each one of these areas here, like here we have a triangle, and over here we have another triangle, and on the bottom here we have a square. Those are all polygons. So it has to be made up of polygons to begin with in order for it to be considered a polyhedron. This sphere is not, it's made up of, circular regions, and this one is too, so it's not a polyhedron. And it has to be simple and closed to begin with, so these 2 are out automatically. Now, we call the space, let me get down here to a better picture for you. We call the space where the sides or the faces is what they're called, where those meet we call an edge, which kind of makes sense if you think about it. We call each one of those sides, top, bottom, back, front, up and down, those are called faces. And where 2 of the edges or more meet, we call that a vertex. So that's that point right here. This happens to be a figure called a right triangular prism, and we're going to learn why it's called a prism here in just a minute. But because of the way that it being a prism means that it has to have 2 parallel bases. So here these are called the bases, special kinds of faces, and the everything around the side is called a lateral face. So we'll see that here in some next few pictures. What makes a prism is that it's a polyhedron in which 2 congruent polygonal faces or bases lie in parallel planes. They are usually named after the bases. So here's the picture that we were looking at a while ago, and we have triangles that are parallel to each other, and then everything else around it would be called a lateral face, but these are parallel. Here we have 2 squares or rectangles that are parallel to each other, And then here we have two hexagons that are parallel to each other, and then rectangles all around the sides. And then here again we have hexagons, but do you notice that these hexagons are kind of slightly off? They're like kind of skewed sideways. This is called an oblique hexagonal prism. The others are called right prisms because their lateral faces and their bases form right angles to each other. So the faces other than the bases are called lateral faces. If they form right angles with the base, then it's called a right prism. If they do not, it's called an oblique prism. So that's how we know that something is a prism, because they have those parallel bases, and then they can either be right or oblique. And we always name it using those bases. Whatever the base is what it's called. So this one would be a quadrilateral, right quadrilateral prism. We could even call it a right rectangular prism, or if all of these sides were equal length, it would be a right square prism. So sometimes they can have several different names. Now, there are other types of polyhedron, mainly these pyramids. Prisms and pyramids are kind of, I think, the coolest ones because they're the interesting ones to name. A pyramid is a polyhedron with a base of any shape and then an apex, which is a point that's off the base. Triangles are then drawn from the apex to the base. Pyramids are also named using those bases. So what I'm talking about here is, let's say this is our base. This was a triangle. Then you have a point that is drawn off of that base, and triangles are drawn from that point to the base. That's what makes it a pyramid. This one would be a triangular pyramid because it has a triangular base. This one would be a square pyramid because it has a square base. This would be our apex, and then the triangles drawn off the apex to the base. Here again we have a pentagonal pyramid, which has a pentagon as its base. And again, here would be our apex with our triangles drawn off of the apex and down towards the base. So that's kind of cool that you can name things that way if you understand the structure of it. Here's some other kinds of cool polyhedra. These are called regular polyhedra because all of their sides, all of their edges are the exact same length. So it's kind of like our regular polygons that we had. If you'll remember, you had like a equilateral triangle was a regular pentagon. I'm sorry, a regular polyhedron. Polygon. Let me get my words straight here. Because all of the angles and all of the sides were the exact same measure. We could also have a regular pentagon, which that's not the best drawing in the world. I'm not the best artist. Or a square is a regular quadrilateral because all of the sides and all of the angles are the exact same measure. Well, we have something similar in polyhedra. A tetrahedron has four faces, and again, each one of these edges is going to be the same length. A cube has six faces, so we have four sides, a top and a bottom. That would be our faces. This would also be considered a prism because the top and the bottom faces are parallel to each other. So again, it has several different names. An octahedron is kind of a cool one that has 8 faces, and they're all triangular in shape. This is called a dodecahedron. It has 12 faces that are all pentagons in shape. And here we have what's called an icosahedron. It has 20 faces, all made up of triangles. Aren't those kind of cool? Here we have just a table that I went ahead and copied out for you so that you would know some information about some of these regular polyhedra. So we have our dodecahedron that's made up of pentagons. The measure of each interior angle is 108 degrees. With it being regular means that they all have the same measure. There are three pentagons coming off of each vertex, and so on and so forth. So just some information for you about that. And then I also put on here a couple of other cool ones that I just think are kind of neat to say. This is called a truncated icosahedron, so that's kind of cool. But this is probably the coolest one to say. Icosahedron. Have you ever heard of that in your life? Probably not. But it's kind of cool just the same. Here we have some of these regular polyhedra that how the vertices, the faces, and the edges are all related to each other. There's something called Euler's formula. Let me write that out there for you. Euler's formula that relates regular polyhedra's vertices, faces, and edges together. And that formula is the number of vertices plus the number of faces minus the number of edges has to equal 2. And if you'll notice in this table, each one of those situations that is true. If you add up the vertices plus the faces and then subtract off the edge, you end up with 2 each time. Now our final ones that we're learning to name are cylinders and cones. Now these are not polyhedral because remember they have to be polygons in order to be called polyhedral. But they're cool just the same. The cylinders are made up of two bases that are parallel to each other and they happen to be circles. And then it's as if we have all of these little bitty teeny tiny rectangles that are infinitely small that have been drawn around this. If you were to open this up, it would be a gigantic rectangle. And this one happens to be a right one because the lateral surface forms a right angle with that base, which is a circle. Here we have an oblique circular cylinder because again it's not right, then it's oblique, meaning that it's kind of skewed just a little bit, but notice that the bases are still parallel to one another. This one would just be called an oblique cylinder because it's not circular, but the bases are parallel to each other, and then it's been swung around for our lateral surface. For cones always start off with a circle as the base, and then again we have an apex, a point that's drawn off of the base, with all of these infinitely small triangles drawn all the way around it so that it's connected. And these triangles, you get them smaller and smaller and smaller until it's all connected. Now we can have right circular cones, which mean that the altitude, the line that's drawn from the apex to the base and forms a right angle with it. If that happens, then it's called a right circular cone. If you draw, or I should say perpendicular to the base, if you draw from the apex perpendicular to the base and that happens to hit outside of the circle, then it's an oblique because there again it's skewed in nature. Oblique always means kind of sideways, so you can kind of think about it that way. I always think about your oblique abs as being kind of on the sides of your body, so it's kind of sideways. Okay, let's do a couple of quick examples before we're finished. This one says identify each of the following polyhedra. If a polyhedron can be described in more than one way, give as many names as possible. So our first one, because we have a base and an apex that's drawn off of the base, triangles drawn from the apex to the base, we know automatically that has to fit the definition of a pyramid. So we know it's some kind of pyramid. And if you'll remember, pyramids are always named off of their base. So this base happens to be a rectangle. So we could call this a rectangular pyramid. It might be a square pyramid. In fact, we don't really know to be certain, but it could be. The second one here, again, we have two bases that are parallel to each other, so that fits the definition of a prism. And in this case, these happen to have four sides, so this would be considered a quadrilateral prism. It looks very much like these might be trapezoids, so we could call it a trapezoidal prism. This one, our third one here, part C, is we have a base, and again we have an apex that's drawn off of that base, triangles drawn down towards the base, so that fits our definition of a pyramid again. And pyramids, remember, always named using their base. So what kind of a base do we have here? We have a five-sided figure, and that's a pentagon. So this would be considered a pentagonal pyramid. Alright, here we have a tetrahedron, and they are asking us to name the different parts of it. So part A says name the vertices. Well, our vertices, remember, are where those edges or the edges meet. So here we have one at W, we have one at A, we have one at R, and we have one at D. So those would be our vertices here for this tetrahedron. Now what about our edges? Well, we have edges. Here's an edge from D to W, so that would be written as DW with a line over it, meaning that line segment. We have DR, we have RA, should be putting the lines over it, and we have AD. We also have WR, and then lastly we have WA. Now finally it's asking us for the faces, or not finally, but for vertices, edges, and faces. These kind of always go together. Faces happen to be, in this case, because it's a tetrahedron, they would be triangles. So we have this triangle, which would be considered, we can name it any way you want to, you just have to name it in order. You can't, you want to make, just be careful about how you name it so that you're always, if you draw it, do it in that order. So I drew this as WDR. So I'm going to write that. I'm going to write it down here as triangle WDR. And then we also have this front triangle here, which I'm drawing as WRA. So that's triangle WRA. Now I don't know if you can see it as well here, but we also have this backside triangle, WDA. Triangle WDA. And then finally we have the base. And the base here is DAR. So that would be triangle DAR. So you may want to do those in colors so that you can see the different ones as you go through this. Okay, finally here, last two questions. Intersection of face DRW. So DRW is here. This is the face. And the edge RA. So let me do that in a different color. The edge RA. They want to know where those things meet. Where do they intersect? Well, that would be only right here in this one point of R. And then lastly, the intersection of face DRW. So again, DRW. and another face DAW. So DAW is that back side there. They want to know where those intersect. And it would be right here in this line is where we overlapped this line DW. This line segment. Now you could label it as WD also, and it would technically be the exact same thing.